Right. Welcome, everybody, to Advancements in Angular. My name is Jeremy Elbourn. I am a member of the Angular team at Google, and I'm the tech lead for the Angular components team, which works on Angular CDK and Angular Material. And so I'm going to start today by looking back in time, 3 years to 2016, when we had a big celebratory meetup in Mountain View. And this was a celebration of Angular 2.0 finally coming out. It has been 3 years since that release, and a lot of things have changed in the framework since then. And I'm going to be talking today about how specifically the framework has advanced. But before I do that, I want to talk a little bit about something that hasn't changed with Angular, and that's the values that are held by the team. And we really aim to build a framework that developers love to build applications with, and let them build applications that people love to use. And we want this development ecosystem to take place in a community where everybody feels welcome. The community for Angular is huge, and it spans the entire globe. The number of conferences happening around the world is always going up. In 2019 alone, there have been 7 new events that we know of, which brings us to over 24 annual conferences. And on top of just conferences, there's something in the neighborhood of 780 local meetups happening around the world. On top of that, we have 105 Angular Google developer experts now that share their expertise via blogs and podcasts and videos and talks like this one. And there's an organization out there that the team is really proud of called NG Girls that aims to foster diversity in the tech world by training new engineers with Angular. And this experience can be really transformative for attendees. They have run 25 workshops in the last year with over 700 participants. There have been over 250 mentors who have volunteered their time towards this effort. And they have more events planned going on through the year and into next year. So it's really great to see this continuing. And all of these people we see building Angular apps and participating in the community, they are building all sorts of different things. We see, complex business things like airlines and business administration, financial services, retailers, and more. Things like team dashboards, small applications, documentation sites, we see it all. Whenever I'm browsing around the internet, I'm always popping open DevTools to look at what is this made with? What's that? And recently I was surprised to find something new built with Angular I thought was pretty cool. Microsoft has this new Mixer streaming platform that's kind of like Twitch. Then this is a web UI built with Angular. I thought that was pretty interesting. And inside of Google, as about a year ago, we had about 600 projects inside of Google using Angular as of September 2018. And jumping forward a year to September of 2019, there are over 1,500 projects in Google using Angular now. And this includes some really big applications inside of Google, like the Google Cloud Platform Development Console is the largest Angular app that we know about. And we're really happy about this continued growth, even though it does make our job a little bit harder in rolling out updates inside of Google. You'd be surprised at the weird things people can get up to with their Angular applications sometimes. And so kind of keeping all of that in mind, that we have this massive community that is invested in Angular, I'm going to talk about the technology updates that we have had in the past and where things are going in the future. So there have been 7 major releases since that initial Angular 2.0 release back in 2016. And before I get to the newest stuff, I want to talk about where we came from so that there's some context in Angular's evolution, and also to catch you up in case you haven't been following along with the development all of these years. You may be wondering why you don't see a 3 in this timeline. We skipped version 3 just because it was going to confuse people. A lot of people were saying after Angular 2, is there going to be an Angular 3? And no, there's not going to be an Angular 3. But, we were just doing some versions. We just skipped to 4. And let's go ahead and start looking at the original Angular 2. And this is where the vision for the framework really came together, right? It was an evolution of AngularJS, and was built to overcome some of the fundamental limitations in that kind of previous generation framework. It was built to be statically analyzable so that you can check your templates for errors and avoid shipping compiler code to the browser. It had universal semantics, so whereas AngularJS you had to create individual APIs for things like click and double click and mouse over, with Angular there's just one semantic that works for all events. So things like that. Lazy loading and server-side rendering were something that were considered from the very beginning, and we started having CLI tooling to make it easier for people to do local builds and testing and serving without having to kind of come up with their own development environment. So moving forward from there, we hit the 6-month release cycle. We're pretty consistent about keeping the 6-month release cycle, and version 4 is mostly about polishing up things from the big 2.0 release. There's a lot of refactoring that can lead to significantly smaller bundles, a lot of quality of life improvements across the board for APIs that had some rough edges. We continue on. 6 months later, we get Angular version 5. This is where the CLI starts to get some really nice features. There's a build optimizer that can really intelligently bring down people's bundle sizes. And the ecosystem around Angular also starts to develop with improved server-side rendering in Angular Universal. We get a new HTTP client, and we start to get stable releases for the UI component space with the component dev kit, or CDK, and the material design components. We move forward 6 months again, and version 6 of Angular brought one of my personal favorite features about the framework, ng-add and ng-update, which are cumulatively part of a feature we call Schematics. And the first, ng-add, lets you automatically bring a library into your Angular app, and if that library has configured this, do any setup for the library automatically. So an example here is the material design components. They require a theme file in order to run, right? You need to specify what your material design colors are. And if you do ng-add with Angular Material, it's going to automatically set up that theme file for you. It's going to create the file and add it to your application styles. And any library can do this. They can set up a schematic that will decide what configuration needs to occur when you install it. ng-update is an even more powerful tool that automatically updates your version from one Angular version to another. And this really helps the team smooth the transition going from one version to another. A lot of people really just don't like breaking changes, right? You are building an application and you don't have time to deal with a bunch of kind of tedious refactorings or renamings, and this feature lets you just run ng-update, update your version. Everything should be taken care of automatically. Obviously, there are some changes that can't be handled automatically, but even in those cases, the tooling will attempt to find those patterns and report affected code or add it to do. And cumulatively, this can save hundreds or thousands of developer hours from kind of these tedious refactorings. And it was around this time, after the Angular 6 release, that the team started to get to kind of a plateau in terms of what could be done with that iteration of Angular's architecture. And they started, around this time, exploring a new architecture for Angular's internals. And so as we move forward, this is kind of happening in the background. So we go ahead 6 months again to Angular version 7, and we get bundle size budgets in the CLI, interactive CLI prompts. So those schematics I talked about can now ask you questions. So when you install a theme for Angular Material, it can say, what colors would you like in your theme? And you can choose them. And the component ecosystem is also evolving with things like drag and drop and virtual scrolling. So Angular version 8 is the current stable release. It included a really cool feature called Differential Loading, which I'm going to talk a little bit more about, and an ng-deploy command, kind of to match those ng-add and ng-update, and a preview of Ivy, which is kind of this reimagining of Angular's architecture I just mentioned. And this preview is off by default, but it let people opt into a kind of alpha version that people could try out and give feedback on. And so this differential loading, this is a really powerful feature because the way you would historically do JavaScript loading in any application, if you want to support older browsers, is that you, one, have to target an older JavaScript syntax, right? IE 11 can't support modern ES6 or ES 2015, 2016 syntax. And you also need a bunch of polyfills for web features that just aren't supported in these older browsers. And so even modern browsers would have to pay a tax for all of this code they don't really need in order to just make everything work universally. But with Angular version 8, it supports kind of this new approach you can take on the web called differential loading, where you can produce separate bundles for modern browsers and for legacy browsers, where your modern browsers are using modern ECMAScript syntax, bare minimum polyfills, and you have a separate bundle with all of the polyfills and the old syntax, and the browser can decide which of those bundles to request. You need absolutely no server code to do this. The updating of your Angular application will make it so that your client does this automatically, and this can have a really big impact. So on angular.io, our documentation site, which is a relatively simple application, this saved 41 kilobytes for modern browsers, which is a really big improvement. And depending on your application, the savings can be anywhere from around 7 to 20% of your bundle size. So on top of that, we also worked on making deployments easier when you're using Angular CLI. We talked about that ng-add earlier, and there were a handful of people from the community who added different deployments for different cloud hosting providers, so Firebase, Azure, Netlify, GitHub Pages. And this allows you to bring in configurations and setup for those things. And once that's available, you can always just deploy to your cloud provider with ng-deploy, and then really simplifies a workflow that a lot of people have kind of annoyance with. So all of that brings us to where we are now with version 9. Ivy, this is in release candidate right now with the stable version expected in December. And so what actually is in this, right? What are the goals we wanted to accomplish with kind of this big refactoring of Angular's internals? So we want to make things smaller, as we always do, right? You can see this trend line cutting through all of the releases where we're just constantly aiming towards bringing bundle sizes down. We want it to be faster. So there were some opportunities to optimize what Angular was doing at runtime. We want it to be simpler. There are some places where kind of developing on Angular can either be complicated or confusing, and so we want to simplify things where we could. And most importantly, backwards compatible. We talked about Angular's huge community and all the people who invested in this, and it would be not cool to require all of those people to do some kind of major rewrite or refactoring in order to deal with an architectural change. And so the team has put in a massive amount of effort at making this refactoring, this re-architecture, as backwards compatible as possible, to the point where most applications shouldn't notice any major differences. So that's a lot of really ambitious goals. How does Ivy accomplish all of that? How on earth is you going to get all of these things? So let's dive into some of the more technical details of how Ivy is going to accomplish some of this. And we're going to split this into two parts. We're going to look at the Angular compiler, which is what you're building before you actually end up with your JavaScript bundle that's running in the browser, and the Angular runtime, which is the code that actually runs in the browser. And we're going to start with the compiler. So why does Angular need a compiler anyway? You may be wondering, if you're not super familiar with it, isn't a web framework just a bunch of code that runs in the browser? Well, it's actually a little bit more complicated than that. So if you have an Angular component like this, and actually, can I get a show of hands? How many of you have actually used Angular or have some familiarity with it? Okay, a lot of people. So I'm just kind of assume baseline knowledge here. So we have a UI component here, it's pet profile, it has kind of a simple HTML template. And if we take a step back and we look at this from an ecosystem perspective, we can see some things here that aren't exactly standard. So first we have this component decorator. Decorators are not an ECMAScript standardized concept, although they are supported in TypeScript. And we also have this HTML here, and while this is valid HTML per W3C specification, there are some things in here that have special meaning to Angular, right? We have a text interpolation, we have a property binding, and in regular HTML, these would just be inert attributes, and you would see curly name in your template. And so Angular is actually adding some special behavior based on these things. And so the main thing the Angular compiler does is take these constructs and turn them into JavaScript code that's going to run in your browser. So the compiled code for this component is under Ivy going to look something like this, where we're adding a static ng component def onto this class that we're decorating. And this component def has all of the information around the Angular stuff for this class. So you can see the selectors. It has a factory function, which is used by Angular's dependency injection to construct things. And there's a template function here. And this template function is the main thing that the generated code is responsible for. So your HTML templates are being turned into JavaScript code that is going to render and keep those templates up to date. And so I'm kind of hand-waving this JS code here because we're going to look at that in a little bit. But one improvement I do really want to call out that's a big part of Ivy is that the generated code for this class is actually emitted into the same file on the same class in which it was authored. This is an improvement over previous versions of Angular where the generated code for this component is emitted in a separate file, which was called an ng factory file. And the team was able to make this change thanks to a relatively new API introduced in TypeScript 2.3 that let the framework alter files emitted by the TypeScript compiler. This really simplifies one part of the framework because now you never have to import a generated file into your code. So previously, if you were bootstrapping your Angular application, you would have to reference this generated ng factory file, and sometimes IDEs like that, and it's kind of weird. So you won't have to do that anymore. You always know where to look for the generated code for any given component. It's always in the same file. And framework APIs that treated components and ng factories as separate constructs now just have to know about one thing, which is your component class. So you have simpler APIs in some places. So if you ever used component factory or resolver in Angular, the need for that just goes away now. Component factory resolver was an API where you could give it a component and you get back the ng factory, which then you need to use to instantiate that component. Now you can just do all of that with just the class. And so the generating the code in the same file makes this much easier, but the code that we actually generate is improved as well. So we're going to take a look at what some of the generated code looked like in previous version of Angular. So if we go back to like Angular 8, we called the previous version View Engine. And you've been looking at this for a few seconds now, and if you feel like me, this seems pretty opaque. There are some functions that you don't really know what they're doing. There's a lot of magic numbers. There's a lot of nulls, and it's not pretty. But there's one thing I kind of want to focus on in this generated code. There is a line here that is instantiating an ngIf, and ngIf is the API in Angular that can hide or show some portion of your template based on a condition. And you'll see two tokens referenced in here, two symbols, viewContainerRef and TemplateRef. You don't need to know what these are other than knowing that these are the dependencies of that ngIf directive. And this actually implies something about the way Angular generated code in these older versions, which is that whenever you had a dependency on something like ngIf, your generated code also needed to know about the dependencies of your dependencies. And so there was this kind of bleeding of dependencies from different parts of the framework in this generated code. And because of this, you ended up in a situation where whenever a component changes, the Angular compiler had to do a lot of reanalysis and sometimes recompiling things globally, because it didn't know when you changed your component if ngIf had changed, and then if its dependencies had changed, and so on. And this could lead to slow incremental builds. And so going into Ivy, there is this new architecture that brings what the team refers to as locality to this generated code, where each component only knows about its own dependencies. So we saw that factory function earlier in the generated code, which is how a component is instantiated in Angular. And you can see here the directive def for ngIf is the thing that knows about its own dependencies, and anything that uses ngIf is just going to call this factory function and doesn't need to know anything about these dependencies. So whenever you make a change to a component that uses ngIf, you no longer have to reanalyze the ngIf itself. And so this is one part of that the locality as the generated JavaScript code, but there's also a separate piece here. The TypeScript compiler, whenever it is compiling TypeScript into JavaScript, it also produces another artifact called a DTS file, which is a definitions file that contains all of the type information about the code you compiled. And TypeScript does this so that when you are consuming some already compiled code, you can do type checking against all of that code's APIs without having to do any kind of reanalysis or reparsing or anything. And this lets people publish their JavaScript files and their DTS files to, say, NPM and consume that without having to recompile the original sources. And so under Ivy's architecture, Angular actually does the same thing and includes its own type information into that DTS file. So if we look at the DTS file for that component again, we'll see we have our static ng-component-def here included in the DTS file that includes type information about the Angular APIs associated with this thing. So its selector, any inputs or outputs it has. And you can then take the compiled JavaScript file, which has the generated code, because we know it's all in the same file now, and the DTS file, which has the type information, and deliver that all to NPM. And this means that whenever you are going to consume some third-party library, you will never have to recompile those third-party inputs in your application. So previous versions, Angular would deliver something called a metadata.json file to NPM, and then all of the creation of Angular's generated code for templates and dependency injection would happen at the application level. So your application build was doing work in order to create JavaScript code for third-party libraries or separate build units, and now at the application level, you're only going to be building your application code, and there's future enhancements where you can split up your application into further buildable units so that your incremental builds can get much faster. Another part of what the Angular compiler is doing is template type checking, and this is where that DTS file kind of comes in as well. And we've got a pretty complex expression here, and a lot could go wrong with it as we're authoring this template. So we could take a quick look through just to kind of get an idea of what could go wrong with this expression. So first, we have this account view element. So we have to make sure account view is an actual component that exists and that has an input called account. We have to make sure that this getAccount function exists and that it takes 2 arguments of the appropriate type. Because this async pipe is here, we need to make sure that this getAccount expression returns either a promise or an observable. And because of the because this user ID is we're dereferencing this ID off of user, we need to check that it has that property. And this async pipe also implies that the account has to accept a null value as its input, since the async pipe will return null until the promise or observable resolves. And that's a lot of stuff. And as it turns out, Angular's expression syntax is not actually full JavaScript or TypeScript in and of itself. It's actually its own custom thing. And that's so that it can support features like null-safe dereference and pipes, although TypeScript 3.7, which just came out, has the null-safe dereference as well. So how does Angular go about doing this? Previous versions did some type checking, but it wasn't as robust as it could be. And so Angular manages this type checking by, surprise, generating more code. In this case, we're generating something called a type check block, which looks something like this. So we have some function. You can see there's a reference to the account view component. There's a reference to the async pipe. And here's the expression that we're evaluating for that account. So we're assigning account equal to the pipes transform. We're calling the getAccount function, passing the arguments to it. And with this type check block, we've generated some code that TypeScript can just check, and the semantics match Angular's own APIs. So we had this, property binding here that's just turned into a property assignment in TypeScript code. And this code exists exclusively for type checking purposes. Developers will never see it, and it's never compiled to JavaScript and run in the browser. It's just for type checking. So one of the improvements in Ivy, if we zoom in on this a little bit, we'll see it doesn't just have that generated code, it also has these comment blocks in it. And these comment blocks are offsets into your HTML template that map this generated code back to your original template. And this mapping is much more accurate under Ivy than it was with older versions of Angular. So if you had used this feature of Angular in the past, you may have run into some cases where it said, hey, you have some error, and the error was there, but the line number maybe wasn't right or the column number wasn't right. And under Ivy in version 9, this is going to be significantly more accurate. And another major shortfall of the type checking in the past was that it wasn't able to handle generics. So if you had some directive or component that used a generic, it would just totally bail out. And the worst offender here was ng4, which was Angular's way of repeating over content inside of a template, one of the most basic things that you do. And this ng4 directive is a generic. It is ng4 of t, where t is the thing that you're iterating over, is the type that you're iterating over. And with Ivy, Angular now has the ability to infer types on these generics by generating extra functions that allow TypeScript to just pass through the types. And so we can see here, Angular has generated a function, ng4 type, that takes in an array of t and gives back an ng4 of t. And the way TypeScript works, if you call this function and you give it a type where it knows what this t maps to, you'll get that appropriately mapped t coming back out of it. And so based on this, Angular will be able to now type check all of your templates instead of bailing out whenever you got inside of an ngIf, which is a really big improvement and really helps make developer productivity a little bit better without getting errors and having to fix it and rebuild. So that about wraps up what I wanted to talk about with the compiler. We saw that it's hopefully a little bit easier to understand with generated code in the same file, faster to build based on splitting up things into the DTS and JS files and having more strict locality, and that it's safer to write with the template type checking. And so now we can move on to Angular's runtime, the code that runs in the browser. So we've talked a lot about this generated code. So let's actually get into what this generated code looks like. And so we're going to zoom in on this template function here to see what it looks like as your template gets turned into code and run in the browser. And so you can kind of see right away, without really diving into it, that this code seems much simpler than previous versions. So let's go ahead and take a look at that previous version code again. Here it is. I don't like looking at it, but I can come back here and say, like, oh, this looks something I could actually understand. So this generated code is split into two parts. There is a creation block and an update block. And so we're going to go ahead and zoom in on this creation block and see what's going on here. So we have some very simple functions. We have element. We're saying image, source, photo. So this is creating an image element. It is setting the source attribute to photo.jpg as its value. Pretty straightforward. Then we're calling element start. It opens an h1 tag. Text creates a text interpolation binding. Element n closes that h1. Element creates an info card element. Element creates a footer element. And that's it. We're done. That's really as simple as that. As Angular is running these instructions, it is also updating its own internal data structures to keep track of all of these elements. And Angular then uses its own internal data structures later for doing change detection and updates. So obviously this is going to get more complicated as components add more features and inputs and outputs and things like that. But at a fundamental level, it really does kind of stay as easy to read as this. We can even look inside one of these instructions, and we'll see it's relatively simple. This code is going to look something like this, where this element is really just creating the element, getting its parent, setting its attributes, appending to its parent, and updating its internal data structure to keep track of this element. This internal data structure is called an LView. L stands for logical. And so Angular has kind of this logical view of its tree of components. And you'll see that it's actually just setting that element into the particular index of an array, right? This data structure is an array. And yes, it actually is one big array that holds all of the elements, binding values, and directive instances for this component. And this is surprisingly one of the larger optimizations in Ivy. The team has put a lot of painstaking effort into reducing memory use by allocating significantly fewer objects and instead using a system for knowing which values reside in which indices. And so you can see the numbers on the left-hand side here, the 0, 1, 2, 3, 4. These are actually corresponding to indices in this array. So the generated code knows where each particular bit of information is supposed to go. And this LView as a whole looks something like DOM elements, followed by binding values, followed by directive instances. And for this example, we're going to have in it our image, the h1, the text node that we create, and those other elements. And so now that you know about that, we can go ahead and look at the second part of this generated code, which is the update block. So if we zoom in on that, we'll see there's some stuff here that also looks pretty straightforward. There's a text interpolate instruction that you can probably guess what that does. It updates your text interpolation. There's a property instruction that's going to update the property on a node. But there's also this instruction here called advance that it's not immediately obvious what that's going to do, but we can make it more clear by looking at this update block side by side with that LView we just talked about. So when we start running this update function, we're going to have a couple of indices set to different points in our LView. We're going to have a node index, which is pointing to the first node in this view, and we're going to have a binding index, which is pointing to the first empty spot after all of those DOM elements. And so we're going to go ahead and start running this function. We get to this advance instruction, and that's going to advance the current node by 2. And this happens because we need to go to the first node that has some dynamic expression about it, right? Something that Angular needs to update. And once we get there, we're going to run this text interpolate, which is going to get the value for that interpolation, fill it into the node, and it's also going to keep track of that value here in the data structure, and then advance that binding index to the next slot. And Angular is keeping track of these values so that later when it does change detection, it can see if the value changed and it needs to update it. So then we advanced 1 onto the next node that has something dynamic about it. We're going to call this property value and that property instruction, and this does the same thing where it's getting the new value and storing it, advancing that index, and then we're done with our update function. If we later come back and run this again and we get to our text interpolate, it's going to use that value from the LView to check if it changed, going to do the same thing for the property. So this update block can get called multiple times throughout the lifecycle of the Angular application, while that create block is only called once. And the change detection here, as we're calling this update block, you can see that the components and the nodes, they're checked from top to bottom. So these instructions are, you can see how Angular goes through node by node and update things. And this is really nice because now on a node by node basis, you always know how your DOM is going to get updated. It's going to be in this order of things were written. In previous versions of Angular, this wasn't always the case. The bindings would be resolved in kind of this weird order. Here, they would have been resolved in the order 3, 4, 1, 2. And that was just due to the internal implementation details of the framework, and it had kind of its own weird way of generating code that led to this. So now this is much more predictable. It's also worth calling out, though, that the order in which properties or attributes are set on any individual node is not guaranteed. Those do not happen in the order in which they're written on the template. I want to make that very clear because Angular does an optimization now at Ivy called property chaining, where if you have an element that does have multiple properties or multiple attributes on it, in the generated code, instead of generating code like this, where we'd say property, property interpolate, attribute, property, attribute, it's going to coalesce the similar instructions so that it's chaining them. So all of the property calls are going to happen at once, all of the attribute calls are going to happen at once, and the instruction returns itself so that these can be chained. This is a little bit of a micro optimization. It's just saving a few bytes, which each of these coalesces. But over really large applications or very large components, it does actually save an amount that can add up. And so overall, this architecture of using kind of this instruction set can really make smaller bundles. So we can break this down into kind of different types of applications, and there are two aspects that lead into this having smaller bundle sizes. So first, those instructions we looked at are very granular. Angular has something about around like 150 of them now, the instructions like text interpolate and property. And if you don't use a particular syntax or feature of Angular, the instructions for that feature aren't going to end up in your bundle. So if you don't have text interpolation anywhere in your application, then you're not going to get the text interpolation expression or the instruction, and your bundle will be that much smaller. And so this means that really small applications tend to get smaller because they're just using less of the framework, and so they have to pay for less of the framework. On the other side of the spectrum, for large applications, this new instruction set-based architecture for generated code ends up being more compact than what Angular was doing before. And so the more components an application has, or the larger components it has, the more size savings it's going to have. And we've seen for most large apps, this tends to be around a 40% size decrease overall. So for medium applications that are using almost all of Angular's features, but don't have very many components or don't have very complex components, the size is roughly on par or slightly larger than it was before. This measurement, though, was taken about 3 or 4 weeks ago with one of the 9.0 Next releases before we got to RC, and the team should be on track to bring this down for medium-sized applications so that it's on par with what it was before, so it should be about the same. Another thing I haven't really talked about very much so far is dependency injection. So we saw this factory function here earlier, and I don't have time to go into full depth about how the dependency injection system is going to work overall, but I do want to capture one particular aspect of it just because I think it's personally pretty cool. So Angular has a component injector system where your injector is hierarchical. You can have multiple instances of the same token in your hierarchy. And when you try to inject something in that hierarchy, you're going to get the closest instance from above where you are on the DOM. So if you have some template that looks like this, where you have component A, and inside of it, it has component B and component C, any one of these components can try to inject something, and it's just going to go up the tree and find the closest one that's provided at any particular node. And every one of these nodes has the ability to provide things for injection. They can set some token with some associated value. And you end up with a tree that looks like this in this very simple example. And so if component B tries to inject something, it goes up, checks component A, and then it's going to check your root application injector. And obviously component B can't inject something from component C because they're siblings, right? It only goes up the tree. And you can kind of imagine maybe a simplified version of each node here acting as an injector where it has some array of tokens, right? Some array of things that it's providing. And it has its parent, right? A reference to the parent, so you can traverse up the tree. And a naive approach to doing this dependency injection might be to start at your current node injector, search for the token. If it's not found, you go to your parent, and you just kind of repeat that. And there's actually some opportunity for improving the performance of this. So if we only search any particular node, if we're reasonably sure that the token we're looking for is there, we can just eliminate a lot of unnecessary work. And we can try to do that by tracking the instances of our injectables, our tokens, as we create them, and then associate those instances with the particular node. So what we're going to do is whenever we create something that can be injected, a component or a service, we're going to assign a unique ID to that thing and then record that ID on a particular node in its injector. And then whenever a token is requested, we're just going to continue starting at the current node, and we're going to check that ID to see, is this ID here? And then continue. If it's there, we get it. If it's not there, we go up. And so we're just cutting out some unnecessary work by looking at these IDs. And here's an example where we're going to go down our tree and create things. So we have component A, we're going to give that ID 0. We're going to say that's providing some injectable service A that has an ID of 1. So we're going to instantiate them. We're going to push them into our array. And we're going to record that 0 and 1 are here on this component. And I'm just kind of hand-waving about how we're doing that right now and get back to it in a second. Component B is going to get created. It's going to get an ID of 2. And when it creates, let's say it tries to inject component A. And so it's going to look here to see if ID 0 lives on this node. We know that it doesn't. We're going to go up. We're going to see that ID 0 is here. We found it. We return it. We build this thing and continue. And so you might be wondering, well, wouldn't you just use a set or a map for this? That seems kind of the obvious thing, right? But the Angular team doesn't actually want to do this because those data structures actually use more memory than they're comfortable spending on this. And so rather than using the traditional approach there, they're using something called a Bloom filter, which is a probabilistic data structure that can determine whether an item is either definitely not in a set or maybe in a set. And so the way this works is at each point in the injector, each node, we're going to add just an extra field, a number, just a single number. So a single number, that's not taking up very much memory at all, so that's good. And this number is actually a bit mask. And if you're not familiar with bit masking, you can kind of just imagine that this is a number with 32 different slots, and each of those slots can be either a 0 or a 1, either on or off or absent or present. And since it's JavaScript, the number is 32 bits, so you got 32 slots. And each of these slots is going to correspond to one of those IDs we're creating for an injectable. So slot 0 is going to be in that first positions, ID 1, ID 2, ID 3, so far, and so on. And we can mark that any given ID is present in this node by just flipping the bit based on that slot. And so we can do that just by taking 1, shifting it over by the ID, and logical ORing it with that position. Oops, wrong direction. And so now we can see as we're going through and creating this, and we're creating these instances, we push them, we just do our logical OR with the IDs, and we update our bit mask. And so now when we have component B here going to look for component A, and it needs to check whether or not it lives in this node, we have this bit mask here at B, and we can just immediately check with a single bitwise operation and know for sure that that thing is definitely not in node B and go to our parent without having to look through anything. And obviously this is a simple case, but in real applications you can have a pretty significant number of things to look through on each of these nodes, so this is a pretty decent performance saving. And we can see we go up, we check our bit mask, and we find that the thing is there. And now all of this kind of raises an obvious question. Well, you only have 32 slots. What happens if you run out? And that's where the probabilistic part of this comes in. So when you run out of slots, you can just wrap back around to the beginning with a modulo. And this means that you have multiple tokens that are potentially sharing a slot. And this is why whenever you check, you know that something can definitely not be in a position and skip it. But if it is probably there, then you actually have to go through and search for an exact match. Now, you can adjust the size of your Bloom filter to reduce collisions. Angular actually doesn't use just one number, it uses 4, so it has a total of 128 different slots, which for most applications should be plenty. However, in the case of a collision, it does still fall back to looking. And so why is this interesting? I find this really interesting because I think it's uncommon to see probabilistic data structures like this in the front-end space, and it's kind of a creative solution to a really specific problem. And I just really like seeing kind of these things you learn in computer science class show up in real life. A lot of times you're taking traditional CS classes, you're saying, when am I ever going to use this? This is never going to come up. And here's a place where this came up. So there's a lot more stuff in Ivy and in Angular 9 in general that I'm not going to have time to talk about today. There's a lot of performance work that has gone into strict adherence to monomorphic property access, which involves how the framework generates code that works well with VMs. And there's an optimized unit test environment that helps tests run faster. There are new APIs specifically for console debugging under Ivy, so you can just grab a DOM node and say, give me the component on that node. And that's a much easier debugging experience than anyone had before. And in the UI component space for Angular CDK, we have a new test harness infrastructure that makes it easy to build basically a harness, a handle on any given UI component that works in both unit tests, so something like Karma, and end-to-end tests, so something like WebDriver, and have one uniform interface for interacting with that component the same way a user would, which is really cool. So kind of summing up what we talked about here, Ivy has a new instruction set architecture that can lead to much smaller bundles in most cases. It's faster because it has kind of these runtime optimizations, and the compiler has room to be faster based on this new principle of locality, and kind of a reimagining of how it's organizing its generated code. It's simpler because we're eliminating some concepts and generating code that's kind of much easier to step through, and new debugging tools. And again, backwards compatible. So for the vast majority of applications, they should be able to move to the new version and start seeing the benefits without having any kind of major conflicts. Obviously, this is only a starting point, right? Ivy is still going to be this new thing. And in 6 months, there's going to be an Angular 10 that continues to improve things. You've seen, kind of as I've gone through that timeline, that every 6 months, we hit a new release and we are bringing more improvements and more optimizations to the ecosystem, and that is going to continue. And I'm really excited for that, and I'm really excited about what the Angular community is also going to continue to build with all of this. If you're interested in the things I talked about today, there are some other talks you should check out. My teammate Alex Rickabaugh gave a talk recently called Deep Dive into the Angular compiler. My other colleague Kara Erickson gave a talk called How Angular Works. I drew a lot of content from talks that these people have given in the past. So if you were interested when I'm talking about, these talks will kind of go into that a little bit more deeply. I also want to call out that I am here to talk to you all in the audience. If you want to talk about Angular or tell me about your application or have questions about the framework, I'm going to be around here. I think there's a break after this, so you can just come up and talk to me. And after that, I'm going to be hanging out outside of this room if you want to come find me. That's all I have today, so thank you for coming. If you want to learn more about Angular, you can check out angular.io or see the project on GitHub at angular/angular, and the link to these slides can be found at g.co/ng/devox-be-19. Thank you.